So everything has been very trivial so far. Okay. I was in the middle of writing down an expression before we stopped, and I think I wrote a P, and the alarm rang. So let me see which P in my expression it was. Recap of what I was trying to do. So we still have most of the important expressions here on the board. We want to eventually measure the probability of the cosmological parameters. To be more concrete, we can just think of the set of cosmological parameters as only the Hubble parameter at the moment. Probability of the cosmological parameter given data, the cosmological model, the Lambda CDM model, or the local universe model that gives you a simpler redshift distance relationship, and all the other information. Somebody asked me during the break, what is I? I is all the other assumptions that have gone into the problem. There are many assumptions that we are not talking about. For example, the fact that that there is a gravitational waveform, the fact that this gravitational waveform is described by general relativity. These are all assumptions that have gone into the problem. They're not really very important for us. So for our analysis, we can just leave out I and still have all the expressions in place and do the calculation. But the I is just a reminder that there are various assumptions that have gone in. So we want to calculate the probability density in the parameter space of cosmological parameters given the data and some model. Now, an important thing that I didn't mention and I should have is in Bayesian statistics, all these parameters have probabilities. You can assign probabilities to parameters, to models, so you can define probability densities over parameter space. This is not something that you can usually do in a frequentist approach. So this is the posterior probability density over the parameter space given the data and the model. And that is a product of the prior probability density. And what is the prior probability density? Is the probability density of the parameters that you have, that you expect before you have seen the data. So expectation before seeing the data is the prior. After the data comes in, the probability density is the posterior. And the posterior is the prior times a term called the likelihood, which is the probability that the data is described by this particular set of parameters. There's this term sitting down over here for parameter estimation. This is not a very important term. This is just the probability of seeing the data given the model and the assumptions. So for us, this is only a normalization constant. However, if you want to move away from parameter estimation and go to model selection, then this term becomes very, very important. It is not just a normalization term. That would be the most crucial term if you want to do hypothesis ranking. Now, I said that for independent detections, for independent events, this likelihood factorizes as a product of the likelihoods. This is why we can take likelihoods and multiply them together. So one way of thinking about it is just taking the likelihoods, multiplying them together to get the joint likelihood, and then multiplying it by the prior to get the posterior distribution. Another way of thinking about is you have the prior, and every time you observe something, you multiply the likelihood with it. and then you get a slightly updated posterior distribution. You wait for the next observation, and when the next observation comes in, you can use this updated posterior distribution as your prior. So for each observation, the posterior distribution from the previous observation acts as a prior. That's another way of thinking about it. Anyway, effectively, in the end, you end up multiplying all these likelihoods, and the initial prior that you had chosen, that goes in only once. The rest of the likelihood terms, they go in as many times as you have a number of events. Now I was in the middle of some exercise, which I hadn't really defined why I was doing that. I took this likelihood that the data is described by a certain set of cosmological parameters, and I started expanding it. I started expanding it with the gravitational wave parameters. And why did I do that? That is because I do not really know at the moment how to write this down. It'll turn out that I would know what is the likelihood for the gravitational wave data, for the data, for the likelihood for the data to be described by certain gravitational wave parameters. So a few steps ahead, it'll become clear how to calculate this cosmology likelihood. Okay. Questions? No questions. That means people have understood everything, or people have understood nothing, or a superposition of both. Probability, the likelihood of a single event, given some cosmological parameters, the cosmological model, all the other assumptions. And now I'm going to take the lambda or theta, whatever was there on the other side, and write them out explicitly in terms of the variables that are important for us. So they are the redshift, the distance, the two sky location angles, d alpha and d sine of delta. Again, d sine of delta is d alpha. Is it going too high up? Doesn't matter. D alpha cosine delta d delta. This is the usual measure, so I write it as d sine of delta times. Now I can put in all these variables that I had here. So this is probability of xi given all these things now, z, alpha. Alpha is the right ascension, sign of the declination, and I forgot the distance. So z distance, right ascension, this distance, right ascension, sign of the declination, given omega cosmological model, other independent things. That's the first term. Now whatever I've introduced, I have to put it in. Probability of dl given, so, and probability of everything else that I've introduced. So it has to be z dl alpha sine of delta given omega h I. Whatever stays on the right hand side always remains on the right hand side. Is this expansion correct? So this is the integral, and of course these what do you call them, the volume elements, they are multiplied with each other. They are multiplied with this particular probability density, and they're multiplied with this other probability density. This is same as what I had here. I took this x, I introduced a set of theta, put all the thetas in on the right-hand side here, and another probability with all of them on the left-hand side. And this came from the other expression that I wrote down. Fine? Other questions? Now, I'll try to see which of these things might be dependent on which of these parameters might be dependent on other parameters, which of these things are independent. So, I will need some more space, I hope. This I don't need anymore. I already said that the cosmological model asserts that the luminosity distance is a function of z. I'll write it down again. Cosmological model. It asserts that probability of dl given omega hi is just a function in dl at the value of dl that's predicted by this model given these parameters and everything else. Okay? And this is the gravitational wave data. The gravitational wave data, from the gravitational wave data, it is not possible at the moment. At the moment, we are talking about binary black hole-like objects or neutron stars from which it's possible to measure the redshift. From this gravitational wave data, it's not really possible to measure the redshift. I mean, it doesn't really depend on the redshift. So, this gravitational wave, from this first term, I can remove z. That's because in the gravitational wave data, I'm not really sensitive to the redshift. It's either not dependent at all or dependent so weakly that I cannot measure it. The second term, what I can do is I can expand the second term into two terms. I can expand the second term as probability of dl given omega hi times probability of z alpha delta given dl omega hi. Is this part clear? So what I have done is this dl I'm treating it as an independent parameter, so I can take it as a I can first choose this is probability of A and B. Probability of A and B given C is probability of A given B C times probability of B given C. So this is the Bayes theorem that I've applied here. Yes. So this H in the this H indicates that this is the DL as predicted by the cosmological model and the cosmological parameter. I have forgotten a Z somewhere. Yeah. I've forgotten a Z somewhere, so there has to be a Z on top of all these. And this thing is also, you need a Z for a cosmological model. And the I I'm not really writing, it's not very important now. The I has become a nuisance at the moment. Depending on the cosmological model, the value of only DL would be changing, nothing else. Okay? Okay. Now I can use you've said DL alpha sine delta P of. So here it actually has to be, since that, sorry, I didn't write this out properly. Here I have the in the second term, everything here is on the left hand side. This is on the left hand side. If I want to separate it, then this has to be whatever is left on the left hand side, DL given Z alpha sine delta omega HI. So my previous expression was not correct. Okay, whatever is on the left hand side over here has to be on the right hand side on this expression. Fine? And in the second term, there wouldn't be a DL in the right. That is correct. Okay, is this better now? Now I can use this expression P of DL given Z and other things, and DL doesn't really depend on alpha delta, so they factorize. This becomes a delta function. This becomes a delta of DL as predicted by the cosmological model. If I take this delta function and this and plug it in over there, then what I finally get, I'll draw an arrow and try to write it down over here. I will assume that I can integrate over the delta function. So if I integrate over delta function, I'll be left with a dz. The ddl integration would be gone because it would be integrated over the delta function, dz, d alpha, d sine of delta. From the first term, I would get probability of the data given DL as predicted by the cosmological model and Z and cosmological parameters, and the rest of the things would be the same, alpha, sine of delta, omega, h, I. This is the first term over here. The second term, this became a delta function and got integrated over. So this is going to vanish. Okay, DL, the second term became something like this. Then I said that the cosmological model asserts that DL doesn't depend on alpha and delta. It only depends on these terms through this delta function. So this becomes the delta function which I've integrated over. And I'm left with the third term. The third term is now probability of The third term is now this term, and DL is gone. This is very important. Somebody thanks to whoever pointed out that DL should not be here. Now it's probability of Z alpha sine delta given everything else. Okay? Let's look at this expression for a second here. This looks like a prior on all these parameters, Z, alpha, and delta. So it's a prior on the parameters that you would measure electromagnetically. It's a prior on, if you measure some counterpart, then the counterpart is going to have a redshift and 2 sky coordinates. So this seems to be like a prior on the counterpart coordinates. If you observe a counterpart, then you can replace this by the locations of the counterpart. These things will also become delta functions. It's going to be a delta of Z minus ZC times a delta of alpha minus alpha C, delta of sine delta minus sine delta C. Fine? And the first term is this looks like an expression for the gravitational wave likelihood given some gravitational wave parameters. All these are only gravitational wave parameters, where we have just plugged in the value of the distance that would come from a certain from a certain Z and a cosmological model. Okay? This is a term that is, I didn't go into a lot of gravitational wave data analysis in the morning. I just told you the basic bits. This gravitational wave likelihood function is well known and well written out because we know what kind of noise we expect in our gravitational wave detections. So this particular gravitational wave likelihood, P of x given theta, is just proportional to e to the power minus some inner product of the data minus h some kind of a norm squared, and this norm is with respect to some gravitational wave noise. So this likelihood is something that is known, that we can evaluate because we know what is the detector noise. Okay? Questions? I'll write down the final expression. If this now comes from a counterpart, then the counterpart has coordinates ZC, alpha C, delta C, or since I'm writing sine delta C. So if I have a counterpart, then this just becomes the gravitational wave likelihood P of xi given So it is just the standard gravitational wave likelihood evaluated at the counterpart sky coordinates, and for the distance, instead of the where the distance should go, I take in the counterpart redshift, use the value of the cosmological constant that I'm interested in, calculate the distance, and plug that in. This is the counterparts. With a galaxy catalog, or a set of counterparts, let's say let's say we do not have a uniquely identified host galaxy, but a set of possible host galaxies, then that particular integral, P of Z, that particular probability density P of Z given Z alpha sine of delta given omega hi, this is now a sum over all the possible host galaxies. G stands for galaxy over here, and this is a set of host galaxies. For each particular galaxy, you can maybe associate a weight, because you might know that some galaxy might be a more probable host, some galaxy might be a less probable host. Maybe the brighter galaxies are more probable hosts. Maybe you know that some galaxies are dwarf galaxy, and some astrophysical mechanism says that dwarf galaxies are more probable host. So you assign a weight to each galaxy, and delta Z minus Z galaxy, delta alpha minus alpha galaxy, delta sine of delta minus sine of delta galaxy. So if you take this sum over delta functions, what you end up with is sum over likelihoods now. That particular expression would then become sum over all galaxies, with each galaxy given a certain weight, probability of the gravitational wave data, given distance evaluated at that galaxy, and the cosmological parameters, alpha galaxy, sine delta galaxy, and whatever else was there, which was, I think, the only dependence on H was actually here, so I don't really need to carry along the H. I can only keep the I in this expression. Even here, the only use of H was to give me this redshift distance relation, so I can remove the H from there. Is this expression fine? Now you see it's a sum of these probability distributions. That is why when I was drawing these probability densities, and I also had it out on the board, I said that if with one particular galaxy you get a sum H naught, if with a second galaxy you get a different H naught, and it's either one of the two galaxies, then you would get a sum of these two distributions. This is the sum that you see over here over all the possible hosts, and here is the final product. I seem to have erased it, but there's a final product over all the different events. Okay, I think this is where I will take a small pause, and I'll stop talking about all the Bayesian stuff and start showing some interesting figures and plots again, of course, after you have questions. I have integrated out over the luminosity distance, and that is true. Yes, so I have used the fact that this luminosity distance, given the cosmological model, it is just one value that depends on Z, and that I have plugged in here. Okay. Now, so in this analysis, selection effects is something very important, because again, selection effects can lead to biases, since you are multiplying these posterior probability densities a number of times. If on all these figures you have, I mean, if instead of instead of a certain plot, if you have a slight slope where things should be uniform, if you multiply that a number of times, then the slope is going to get multiplied n number of times and is going to become show very sharp features. I mean, it might even kill the actual data. If there's a slight slope on the other side, then that is also going to multiply and it is going to kill the data and blow up the other way. So it's very important to make sure that there are no systematic biases that come due to selection effects. So that is something I wanted to talk about, but ran out of time, but I should still mention that these are very, very important. So the question is, how well can we measure in the future? So these are results from some simulations that people have performed. These are simulations with GW170817-like events. So these are binary neutron stars at nearby distances. By nearby, I mean redshift of less than 0.1. And they have seen that with counterpart analysis and with about order, this is 100, 200, 300, with about 300 events, you can go to below % precision with about 300 170817-like events. And with these kinds of precision, you would actually be able to resolve the discrepancy that I mentioned. Now, the question is, how many sources like this are we going to see? That we do not know because the rates are very uncertain. With the statistical method, things are much worse. That's the blue line. That's the blue line on the top. But you still go down to order few percent, 2 or 3%. There are strong assumptions that have gone in here for these simulations. These are very nearby. So Z about 0.1. How many binary black hole sources are we going to see at so close distances? It's not very clear. This study has assumed complete galaxy catalog. Galaxy catalogs at these distances become incomplete, and because of the incompleteness of the galaxy catalog, we need to add some term that takes into account the missing galaxies, but effectively smoothens out the posterior distribution, so that makes these projections a lot wider. We have also performed a simulation where these, with incomplete catalogs, and this is how things change with catalog completeness, but things still seem to be in control with a catalog that's about 50% complete. Again, nearby sources, but so might be a bit far-fetched to expect very good results. But we do not really know what we are going to see. I mean, we might suddenly start seeing so many sources with counterparts. We might start seeing sources that are black hole sources that are well localized and close by. I mentioned that I'll mention some open questions. I mean, there's the possible, I mentioned a weighting. We are trying some possible weighting with luminosities, and with weighting, weighting can make things better, because probably the sources that you see out there are the brighter sources, so they're the more massive sources, they're the more likely hosts of these binary coalescences. But some astrophysicists might tell you that, okay, the more massive sources are not really the more likely sources of binary coalescences. You actually need to go into the astrophysics of formation of these compact binaries, and you try to put in something that is more motivated by astrophysics. Again, that is not possible at this stage, because the astrophysical models that govern the formation of formation and evolution of compact binaries is not very well determined. Maybe one can try to do a hand-in-hand inference of both the things. One would ideally like to go beyond the Hubble parameter and try to measure the other parameters, as the Hubble constant, try to measure the other parameters as well. That is, of course, going to be difficult. Even with the statistical approach, the galaxy catalogs become very incomplete. So sources might still be correlated with the visible matter distribution, so one can go to cluster catalogs, which are complete to higher redshift. So there one does not really need to know the redshift of the galaxy precisely, but one can associate it with a certain region, certain galaxy cluster. And since our distance uncertainties are so large, if we are not able to uniquely identify the host galaxy, but if we are able to localize the source down to a cluster, we might still be able to make some inference. These are studies that are planned and in progress and have not been performed yet. Eventually, one might want to construct just a map of merger density as a function of redshift from the cluster catalogs that are available and all the astrophysics that one can assume and put in. There are also some techniques that I mentioned earlier of cross-correlation, using cross-correlation with galaxy catalogs directly, and that might end up being more effective in the long run. Whether that's important, whether that can be important right now or not is an open question. So this is almost all that I wanted to talk about. There are some. I'll put up the slides. These are not. These are some slides from Samaya about gravitational waves. These are basic things about what kinds of frequencies can observe, what kinds of things we can see in various frequencies, and these you can read up probably rather easily, even on other sources. So I didn't go into a lot more detail. Here are some of the other ways that I mentioned of doing gravitational wave physics with either mass distributions of neutron stars or tidal deformations of neutron stars. These are expected to be futuristic at this stage, although people are exploring the possibilities of any of these things trying to be of use in the near future. These are some results from clustering, also expected to be futuristic at this stage. So I wanted to talk about selection effects, which I skipped. I can still try to do that. That is again going to be a lot of probability densities and delta functions. You might not really want me to go into that, or maybe you do. But for the last 15 minutes, I'll take some questions, and people requested me for some references. So I'll try to provide some references for various things. Okay, so the calculation is, if it's a neutron star or a binary black hole, this part of the calculation is very similar, because if you have identified the counterpart and you have identified a host galaxy uniquely, then you do not have a sum here. You just have one single number. However, if it's a neutron star where the counterpart could be from any small set of host galaxies, or it could be any host galaxy in a cone that's come from GRB, or a binary black hole for which there was no counterpart at all, then essentially the method remains the same. The basic mathematics of the method remains the same. Yeah, so I specifically didn't want to go over that, because in most places you hear about match filtering techniques. I had it in one of my slides in the morning. So this is what is happening here is a matched filtering. So these searches that happen at a very low latency, as soon as the data is coming, you have a template bank. A template bank is a set of templates with which you run these searches. And So all these templates, they keep running on the data, and they tell you if there's something that's interesting, and if there's something that's interesting in more than one detector, then you generate something called a trigger alert. People go and see if it's really interesting, or if it's some glitch in the data. If it's a glitch in the data, they veto it. If it's really interesting, they follow it up more seriously. This is where the match filtering appears. While what appears in parameter estimation over here is again a Bayesian parameter estimation like this. So this actually brings me to the question that I didn't answer. I forget who asked the question. Someone. Doesn't really matter. So the parameter estimation here, so instead of estimating the cosmological parameters, what we are trying to do is we are trying to estimate the basic gravitational wave parameters, and the data is the same data, which is x over here. The omega here is not the cosmological parameters, but the sorry for the confusing notation. Maybe I'll change it to theta before I put this up. Omega over on this slide is what I'm calling theta, so it's all the set of gravitational wave parameters. And you can define very similarly posterior distribution for these gravitational wave parameters given data, and that's the prior on these parameters times the likelihood of the data given these parameters, and the evidence is not really very important for us. This likelihood of data given gravitational wave parameters, this term is what's again written out here. So what we observe as a data, let's erase this part. The data that we see in the detector, I'm calling it X, so let me keep calling it X. X is the data that I see in the gravitational wave detector. The gravitational wave detector at this stage, we know that there is a signal over there. It has passed the search. So there is a signal and there's a noise. So this is the data, that's the signal, and this is the noise. Fine? Now, what do we know about the signal? We know about the signal is that the signal is very well modeled by some set of parameters, theta. These are all the gravitational wave parameters, theta, which is by mistake omega on this slide. And there's a noise. So we need to know the signal, and we also need to know the noise. What do we know about the noise? So let me write it in a slightly different way. Let me call this data as a function of x as a function of time, h is a function of time that's also governed by these parameters theta, and noise as a function of time. So you said Gaussian? You said random. Okay, that's one of the words. So random is important. And other bits, what other than random? I ended up saying Gaussian, so that's probably also important. Anything else? Stationary. So the assumptions about the noise is that the noise is stationary. It's a stationary Gaussian noise. So the noise at a certain time and the noise at a certain other time, their correlation function, it depends, it's proportional to some correlation function times only the difference of the time, t minus t prime. Okay? This is what we mean by the fact that this noise is stationary. Okay? Only the difference in the time matters. It's easier to write this out in the frequency domain. So the noise as a function of f and the noise as a function of f prime is, and all these expressions that I'm writing, they're factors of 1/2 or 4 or whatever, I do not remember, I'm writing them from the top of my head. So this is again proportional to sorry, this is not a delta function. The noise, the noise at a certain t and the noise at a certain t prime depends on a correlation that function that only depends on this time difference. This is stationary, and if you go over to Fourier space, that means noise as f and f prime is proportional to delta of f minus f prime times some Sn of f. This is the power spectral density of the noise. What does this mean? That noise at one frequency is not correlated at all with the noise at any other frequency, and at each frequency it is a Gaussian distribution with a certain strength. And that we see in the plot here. This plots the Sn of f. At some frequency, the noise is low, so we are very sensitive at these frequencies. If you go high in frequency, the noise becomes higher, our sensitivity decreases. If we go to the other side, again, the noise becomes louder, our sensitivity decreases. With this kind of a model, I now have a model for noise. I know that the distribution for this noise, that the probability distribution of noise P of n is proportional to e to the power minus some n of f squared over 2 sigma of f, sigma n of f squared. So this is here's the Gaussian bit. We know what the noise looks like. This is the distribution of the noise. It's Gaussian with this particular strength at every frequency bin. Now this noise is just the signal subtracted off from the data. So now we actually know what is the probability of the signal parameters, what is the probability of the signal, or what is the probability of the data described by a certain signal parameters. That is just e to the power minus data minus h as described by a certain set of signal parameters, normed square by a proper way, divided by 2 Sn of f squared. Okay, so this is something we model. So these things, I do not trust any of the numbers here. I'm sure that there are 4 and there are real parts and various things that are missing in these expressions. We can go and look back at these expressions. Some references, that's the next thing that people asked me for. I will try to put the references also on the slides before I send them out so that you have them. Easy enough reference for basics is this review article. It's a review article on this living reviews of physics, so it can get updated every now and then, but it hasn't been updated for a while now. It's a review article by Satya Prakash and Schutz. That gives you a broad overview of gravitational wave physics in general, and also some bits and pieces about how you can do cosmology with gravitational waves. It also talks about how you can do how we can probe the stochastic background with gravitational waves. Then if you want to go into waveform modeling, then the book there's a text on gravitational waves by Michele Maggiore. That goes into the details of the waveform model and all the terms beyond the leading expansion that I wrote down. For gravitational wave cosmology is a very new and emerging field, so there's not really a dedicated text or review article on gravitational wave cosmology yet, so I cannot suggest a ready reference. I mean, maybe you can go back and look at some of the LIGO Virgo detection papers and their appendices. Is there anything else that you wanted references for in particular? Or Bayesian statistics or... Yeah, Shubho is waiting to close the long day. It's been a long day. So let's, if you have any immediate questions, then we can have them. Otherwise, we can. How do I? Oh, we do not get it. We measure it. So the experimentalists, they want to reduce the noise as much as possible. But it turns out that at certain frequencies, there are certain kinds of noises that dominate. At low frequencies, there's something called seismic noise that becomes strong. So you get this kind of a behavior. At very high frequencies, something called photon short noise becomes strong that has this kind of a frequency dependence. While at these frequencies where you're actually making the measurement, there is something called thermal noise, which because the laser, it heats up the mirrors, and that is the main source of noise. Because of these noises, you end up with this kind of a sensitivity curve. And the question is, why is noise, if you have a question, why should noise be stationary? The noise is actually not stationary. It keeps changing. So it's stationary only. The hope is that it's stationary only in the short intervals where you see these signals. So it's a reasonable approximation for these short signals that we see. Even for the long neutron star signal, the noise loses stationarity in between. For much longer signals, the noise is not stationary. You have to fold in for the fact that the noise is losing stationarity. Is the noise Gaussian? Again, the answer is no, but we cannot treat anything that is not Gaussian at the moment. So that's an approximation that we have to work with. Now both Shubha and I are hoping that there are no more last questions.